record. So now we're recording. Welcome back. So I've just finished going over the homework, which I did not record, and now we'll go on into today's lecture. So let me just get the mouse in the right place here. So today's lecture, we went over the homework. That is not part of this recording. And now we're going to talk about outliers, and I've got a number of things we can do. I encourage you, I think it would be a very good idea for you to open up R and follow along. Open up R and try to work these commands as we go. And if you get to a point where it is not functioning and you are not getting the same result as me, please say something. Please stop me. But otherwise, for today's presentation, I have everything on the slides, and I myself will not open R and run the code unless we really get into a situation where you're like, it does not work and you need to show me what's going on here. But I have everything cut and pasted here on the slides for presentation. So let's go back.
Quickly.
Yes.
When do we get the assignments back? Because we didn't get assignment 3 back yet.
No, you haven't. I've been booked and I haven't. I will do it this weekend. I haven't had time to grade those yet. I apologize. I meant to, and it just didn't happen. So yeah, you're owed review on assignment 3, but you will definitely have them both back before our next meeting. I will make the time to do that this weekend. I can do it. So let's go back to this Minnesota data set from a number of weeks ago. Pull this data set up, have this going in your R installation. Same deal, loading it from Excel. Run the head command to confirm that you have the data you think you do. And the only new thing on this command is I combined all my Excel files into one workbook. So I'm pulling this data from the second pane, the second tab of my Excel document. That's why there's a number 2 at the end of this command line. So there's the data. And this is the data set from halfway through where we had already converted the functional class into 3 binary variables. So you see here on the right, we have functional class as three distinct binary variables. We did that about halfway through the lecture on this Minnesota data set last time. And there we go. So let's do the multi-fit, the best subsets fit as a starting point. So again, this is the same as from that lecture 4 weeks ago. Do the multi-fit, get the best subsets fit. And there it goes, and it runs. And I'll just kind of slow down and talk slow and wait a minute while you guys are doing this. I think it's a great idea if you do this while we're talking. So I'm just kind of pausing here for a minute while you run this code or get this model up on your computer. And I'll just pause another second here in case you're typing away. So we want to do this, and then of course that gives you this result. And again, this is exactly the same as the previous, at this point, we're just generating the model with the data from what we had from the lecture 4 weeks ago. We just want this as a starting point. So you have this model, and this was our best fit subset model using GL multi. And it had these 4 variables, and they're very significant. They're all highly significant, and we have a very nice R squared of 0.81, and things looking good, right? So you have this, and then throw up the residual plot, call plot of your model, call plot of the result, and it will generate this plot. And you recall when we looked at this number of weeks ago, I said, hey, look, notice those numbered points on there, folks. And those are indeed potential outliers. They are perhaps more accurately and more statistically said, they are not outliers, but they are significantly influential points. And there's a difference. We don't really know if they are outliers, right? There's no magic mathematical tool that is going to clearly tell us that these data points are outliers. But it's very clear statistically and mathematically that they are influential points. They are points that have a strong impact on the calculation of the model fit. They are points that are significantly moving the direction of the fitted model. And that's why they're really important, because we need to look at them with a lot of suspicion, a lot of concern, and say, wait a minute, guys, these points are really driving the solution to our model. And if we aren't absolutely positive that these points are correct, that they are actually correct data, then we need to remove them because they are causing our model to change in ways that we may not like. So these are those 3 points on the residual plot. They are numbered. The numbers are the row numbers in the data. So number 64 is the data point 64 in the list on your Excel spreadsheet, and 65 and 71. So I've kind of already been saying this. What are we going to do about this? What are we going to do about this? Well, a lot of it comes down to us going back to the original data. And if you don't actually have access to the original data, or you were not the person who collected the data, the truth is actually there's not much you can do, because who are you to say the data is wrong or right? If you didn't collect the data and you don't have access to who collected the data, and you don't have the ability to go ask questions and say, hey, are you sure you typed this in correctly? Then you're stuck. And you just got to use it. I mean, you got to explain to whoever you're talking to about why you think you should take a data point out, because what's your evidence? How do you defend that the data should not have been in there? You have to have an argument, and that argument comes from your knowledge of the business, your knowledge of the environment, your argument. You look at that data point and you have to say, this is not possible. And I'll give you an example. When we're looking at railway timetable data, there are clearly data points that we say, hey, this data point is a mistake. This data point is something really wrong. An example, when the train arrives at the next station at a time point earlier than when it left the previous station, you're like, yeah, that's not right. That didn't happen. There's something wrong with the data collection. There's something wrong with how the timings were put in. Sometimes the answer to that question is things like, if the train driver resets the computer on the train, it like resets the timing collection somehow, and it can generate false data points. Stuff like that, stuff where you look at the timing, the data, and you're like, there's no way this happened. There's no way this train left the station before it arrived at the station. It didn't happen, right? But I've seen that in the data. I've looked at 100,000, a million data points for Coos-Spain, and there's a small number in there, really small number, where clearly what happened is someone turned the computer off and then they turned it back on again, and it like reset, and it collected some garbage data or something like that, and those, then you could argue those are outliers, and you could throw them out. Then you could say, okay, we argue that this data just did not happen. It's just not real. It's not defendable. So we'll throw it out. But otherwise, you have to dig deeper and you have to ask, yeah, well, why did this happen? Why did this data happen this way? So anyway, let's take a look at the analysis of this. So this is a lot of what I already said. So when we talk about outliers, we're talking about strongly influential points. And we're talking about data that's possibly false, that possibly is not real. There are other data points that are also false or not real or entered incorrectly or whatever, but if they are not influential, if they don't actually change our model, we just ignore them. We just don't care. So model points that kind of just lie in the middle of the cloud of data that don't actually change our answer, we don't study them. We don't care. But model points that lie out on the surface somewhere where they are influential, where they really do change things, yeah, we care. And then we need to ask, what's going on here? What's going on with this data? So the method here is, we need to identify the influential points, and then we need to have a very personal discussion and say, okay, guys, what do we think about these data points? Good, bad, what do we do, right? And then we evaluate what the real impact on the model is. And it could, for example, be if we are making a claim, if we create a model and then we're going to go to Dayar, a Politican, with a news release, with some kind of a big news announcement saying, we've discovered this big solution, and there are some significant outlier data points, we would want to verify that removing those data points does not make our claim to the news media false, right? You don't want to discover that the only reason that your big claim to Dayar or to Good Morning Denmark or to, TV2 News, you don't want to find out that that claim is only valid when you've got some junk data sitting in your plot that sits way up here. That's not a good situation. That's not good. You want to make sure that the claim you're making is still valid even when these really bad data points are taken out, because otherwise you're taking a big risk. You're taking a big risk and staking your reputation on stuff that may not be true at all. So let's talk about identifying these strongly influential points. I'm keeping an eye on the clock here. We'll take a break in about 10 minutes, 15 minutes. So we have this theory of outliers. And I scanned this picture here from your text and then and posted it in here. So this is something that's discussed in detail in your textbook on pages 86 to 89. So we're basically just reviewing the contents of those pages here. A big mathematical key to all this is something called the hat matrix. Your text offers the complete theoretical derivation of how this all happens. For us at this level, we don't get too hung up about manually calculate anything or anything like that. We will just pretty much trust the software to do what we want. But the explanation of how the software is working and why it does what it does is here in this theoretical explanation in your textbook, if it's something that's interesting to you. The general idea is influential points are points that lie away from the centroid. So the centroid is let me draw on this. Here we go. There we go. There we go. There we go. So this is the centroid right there. The centroid is the meeting of the average data point on the x-axis and the average point on the y-axis. This is the center of the cloud of data. And we are looking for all the data points that are far away from that point. I wonder if I have I do. Look at that. I have that. I didn't realize that. That's fun. Let's try that. Far away from the center. Oh, cool. I've got arrows. I like that. Look at that. So far away from the center. The farther away from the center you are, the more likely you are to be influential. on the fitting of this line. And let me do this. So this is our line. Well, come on, can I do that? No, I don't, doesn't let me do that. I'll go back to this. This line, right? This is the fitted regression line. And the further away from that centroid, the more, the further away from this centroid, the more you are causing this line to shift. So for example, that point at C right there, it is actually dragging this line up a little bit. It's actually causing this line to rotate a little bit up toward it. So it's like a gravitational pull. This is like the moon at high tide. We got a full moon and the moon is yanking up on the water and causing the tide to shift. And that's exactly what's happening with this fitted model here. So we want to wait. We're going to use the hat matrix and some other things to kind of put a number on this. We want to put a number on these things because it's great to look at the picture and draw fun arrows, but that doesn't really, you know, that's not something you want to do when there's like 100,000 data points. It's not really practical to do that. So we have this thing called Cook's distance. We have this thing called Cook's distance, and Cook's distance is a way of putting a number on how strong these data points are influencing this line. There's a way to kind of put something concrete on this. All right. So this is the Cook's distance for a specific point. So out of the complete data set, point number I or row number I, this is the Cook's distance for that point. And then this is the theoretical formula for Cook's distance. And then this is a mathematically easier one for your computer to calculate, because this one over here requires a complete recalculation of the model for every single point. This one over here can generate the answer once for everything at the same time, which is much better. So we have the Cook's distance here, and your software can generate this statistic, you know, in one big jump when it generates the model. So that Cook's distance is used to generate, is actually what is telling us what those numbered points on the residual plot are. And let me keep an eye on the time here. Yes, we're fine. So the default for your residual plot is to number the 3 largest Cook's distances. That is the default plot setting. And it looks like this. There is actually the plot function has a couple of commands, so you can do all kinds of fun stuff. We'll see some examples of this. But there are a couple of plots from the plot function that do not appear automatically. You have to ask for them. And this is one of them right here. This is the plot, the Cook's distance plot, or the Cook's distance bar graph. And this is plot number 4 in the plot command. You have to specifically ask for it. And but you can see that these are the Cook's distances, and this is the data. These are the rows of data. So this scale down here is what row number in the data set is it? So the 64th data point has a very high Cook's distance, so it has been marked on the residual plot. And the 65th data point has the second highest Cook's distance, and it has been marked on the residual plot. And the 71st data point has the third highest Cook's distance, and it is marked on the data plot. And you'll see here shortly, you can change that. Actually, let's just go to the next slide, because that has what I'm going to say here next. So you can change that, and this command if we add to the plot command this extra bit, we can change how many of the top Cook's distances points are labeled. So if I change this to 5, I get 1, 2, 3, 4, 5 points from that plot right there. And so that's, and then this command is saying I want the first plot figure from the list. And in fact, what is that list? Well, actually, I've got that for you on the next slide here. These are actually the 6 plots that the plot command will give you from a linear model right there. So those are the 6. And there's a fun, I gave you this web link down here. There's a very nice, well-written explanation of this plot command with all of its bells and whistles and options and things. That is very good. So take a look at that if you would like to dress up your plots or do something fun with your plots. And the default, when we run this normally, the default is it gives you 1, 2, 3, and 5. And the ones that I have been discussing with you have been the first, number 1, and the number 3. 1 and 3 are the ones that I have been showing in our slide presentations over and over again. So here's a little more, again, a little more detail about how that plot command works. And this summarizes what I've been showing you about how to customize or get different answers from that plot command. We can also go a little further with a customized plot. There is the plot command for a linear model, and there is just a generic plot command for any old data sets you've got. And it's a little confusing to me, actually, that they have both the same name, and yet they magically know how to behave differently according to the data set you put in. I find that a little bit interesting. I'm not clear how they work that magic, but it does. So the same exact command, if you just change the way you specify the data, gives you a whole different set of possibilities. So even though this is the same command text, the rules and the options for what you can do are totally different if you specify a different data source. So now I am specifying my X and my Y values specifically in my plot command. So here are my X values, and here are my Y values. So this is a custom made plot. I am specifically just making this plot by hand. And this is another fun command. If you take the name of your data set and then type a $sign and then type a column name from the data set, you can just pick one column from the data set and say, take this, here you go. And then over here, here's the Y value. And if I use this command resid and just specify the solution to my linear model, it will just bring out the residuals for that linear model in order that matches the rows of the data. And then these are just labels. These are just text labels. So this is a label for the Y-axis. This is a label for the X-axis. This could be a title if you want to put a title on your graph, whatever. So let's see what that gives us. So I run this command, and this is now a residual plot, but is a customized residual plot because the standard residual plot is the residuals against the fitted Y values. And sometimes you want to look at this in a little more detail. You want a little more deeper thinking about what's going on with this solution. So now I want a little deeper thinking. I want to look at the residuals against a specific data column, not just the whole fitted Y, but I want the residuals against one data column from the data set, because I want to look at more tightly, look more closely at that data set. This is a good point to take a break. So for those of you following along, I hope you've been able to follow along. We're going to take a 10-minute break now. If you've been having a technical problem or you have not been able to follow along, I would encourage you to use a little bit of this break to try to catch up. It'd be really great if you can catch up and have, run the code and have this plot on your computer so that we can go forward and do this together and you can ask any kind of questions. So let's take a 10-minute break now. And when we come back, we will continue with looking at these plots and analyzing what's going on with these plots. So 10-minute break here. And I think that we will go probably end early today, relatively speaking. And but 10-minute break and I'll see you back. Thanks. We're back from break. So here we are. And we have this plot. And so the point of this is very often you can't figure out what's really going on if all you're looking at is the general residual plot of the residuals against the predicted Y. It's just, it's interesting. It's got some data, but all the details are hidden. You can't see the details. So what you need to do, you need to drill down into the residuals against every column of data. And to do this, what you do is you create a panel of residual plots. There are a couple of ways to do this. A lot of software packages have a command where you just say, generate a panel. And I think there's a command in R too, but I didn't take the time to research it. I think there is a command in R, a package really, that allows you to just, in one command line, create a panel of all the residual plots, but I didn't have time to research it, figure it out. So I kind of did it the hard way here. So here's my panel. So here's a panel. You have here a residual plot against each of the 4 variables in the data set. So we have a residual plot against each of the 4 variables. And this is interesting because, you can look at this. Let me get my annotation tool here. Yeah. So, you can kind of look at this and say, where are there really significant things going on with the residuals? And, you look at the, let's start down here at the lower right with this function class 1 variable. And, there ain't much going on here. Not a lot going on. It seems evenly balanced top and bottom. There's not really there's more variance here, but it's evenly distributed, right? I mean, it goes up and down. Maybe a couple of points up here, but otherwise, nothing exciting, nothing really exciting. Same thing over here. The picture is not that much different. If we look at access control, not really any big distribution going on. Not really over here. Not a lot going on. And then we look at the, this is the county population chart here. Yeah, there's something going on, right? Because there's like a little tight concentration here, and then an interesting spread down here. Then it's evenly spread here, I would argue. And then we've got kind of a little bit of a taller tail up here. So that explains why in the previous residual plots, we've seen this kind of red median line doing a dip down and then coming back up again. And the same thing kind of similar going on here. The number of lanes question, not too bad here. This is reasonable. a little bit of a downward swing down here, and then a definite swing up here, and then this one point where it's like, you know, it's a single point, and so there's not a lot of representative data. There's only one data point in the whole data set that has 8 lanes of traffic. So that might be an argument for an outlier, because if you've only, in a whole data set, you only have one data point that has the characteristics of that data point, it's like, maybe that's not really a good fit, you know, maybe because it'd be like, I'll give you an example. It'd be like you took a survey of, I don't know, transport users, metro customers, right? And I'm trying to think of an example here. You do a survey of metro customers, and you have 2,000 responses, 2,000 data points, and 1,999 of these are people who are, you know, basically Shaleners, people who live in Shalen, people, I don't know, anywhere from city center Copenhagen to Helsinger or Roskilde or whatever. And there's one data point in that 2,000. There's one data point. It's like somebody from Finland, right? And so when you're trying to, and they suppose they answered all kinds of questions. I don't know, you know, they gave you all kinds of information in the survey. But you might ask the question, okay, I got all of this data from people who come from Shalen. I got one data point from a guy from Finland. Maybe my data set is going to be all messed up by this one guy from Finland who isn't going to be comparable to all the other data in my set. So might raise a question of, does it make sense to keep that data point in the data set? Maybe it needs to go. Something like that. I don't know. I'm trying to visualize an example. So anyway, so here's our panel of all the residuals. There's a few more tools we can play with just to demo what we can do here. You can do this if you look up Google or look up the instructions on how to use the plot command. There are a lot of fun things you can do. You can add a reference line to the plot with the code. And the way this works is, okay, you call this plot command and the plot window opens. There's a separate window. As long as that window is still open, you can add extra command lines to the R code and run them, and it will add extra graphical elements to the open plot window, and you can draw on the plot window. And it's not until you close the plot window and throw it away that it's all over, that it all goes away. So, you know, here's a command here for drawing a horizontal line on the plot. You can do that, and you can give it an angle. So the first point is where it starts, and the second point is where it ends up here. That's one thing you can do. There's a lot of different kind of tricks you can do to pretty up your plots and make them look more interesting. But let's go back to this outlier conversation. Let's look at this a little more closely. So now we've got some tools. Now we have a way to look at this in more detail. Let's think about what's going on here. We'd like to look at these outliers more closely. Let's take a look. We need a command to do this. We have a command to, we can manipulate our data if we want to do some tighter analysis. And we do this by this command with the square brackets. And if you type the name of a data set and then put square brackets, you can tell it to add or subtract rows, and you can tell it to add or subtract columns like this. So let me show you how that works. So here's an example. So here's the data as it was, and there's the rows 1, 2, 3, 4, 5, 6. And if I type this command, I type my data, square bracket, and then negative. So this is remove. Negative is remove. So remove. C is a command that says create a vector for me. Anyway, negative C parenthesis 2. So I want the second row. And then I have nothing here. This is blank. I'm not going to touch the columns. Not touching the columns, so just leave it alone. So negative C2, and row 2 is gone. It's not gone. It's just not displayed. It's omitted. It's still in the data set, but I'm not using it for this current command. So row 2 is gone. So this is just an example. This is a way we can manipulate this. So now let's fit the model with those 3 rows gone. Let's fit the model. Let's see what happens to the model if we don't include that data. So we're going to run the model here without those 3 data points. Redo the model without those 3 data points and see what happens. See what happens. And if you do that, I'm just pausing a second here. I would like you to try this. So I'm just pausing a second for you to try this, for you to type this in and actually try this. Remember, you can always get an old command back in R. If you use the up and down arrows, you can type the up arrow and it will flip through the previous command lines. You can flip up to a previous command line, and then you can type, you can use the left and right arrows, and you can move your cursor into the text of that command and edit the command and change it. Saves you a lot of typing, saves you a lot of work. So you can recall an old command, make a change to it, and then hit return, and it will issue as if it was a completely new command that you issued from the keyboard. So do this. So if you do this, here's the result. So here's the result after doing that. Okay. And not a lot of change, but let's compare these two. Let's compare about how they change. Let's take a look at how they compare. So there's the comparison. So this is before, and this is after when I omit the rows. And R square, a little stronger. This stands to reason. So by omitting outliers, you are making the model easier. You're eliminating all the bad data points. If you take away the bad data points that don't fit, then by definition, your model fit is magically going to get better. So this should go up, but be careful because it's kind of cheating. It's kind of cheating because, of course, if you're not winning the game, just move the goalposts, right? Just, hey, it's not working. Let's just eliminate that part that I don't like. So that goes up. They're all still, the coefficients are all still significant, very highly significant. Small changes in the coefficients. So not a lot of change, but a little bit of a change. A little bit of change. But the scale of the coefficients, 2, 3, 4, 4, 2, 3, 4, 4. The scale is not changing really. And the small differences in the values of the coefficients, but not a huge amount. So yeah, it's okay. So removing these outliers hasn't dramatically changed our model. It's made some changes, but not a huge amount. And let's go a little further and let's look at the residual plot. And you can see that the general shape of the residual plot has not really shifted a lot. The biggest difference is that the range of the chart has changed, right? So up here, we're at 40 and negative 40. So that's right here and right here. So this whole top half, whole top third of the residual plot is gone in the new model. It's just not there anymore. But the general shape of everything, I mean, not a big change. Not a big change there. Not a big change. Whoops. So depending on what you're trying to accomplish, this is a good thing, because removing these outliers is not changing the fundamental direction of this model. So remember what I said before the break. My argument said, look, you're going to go on TV too, or you're going to go get an interview with Politiken or Berlinsk or Ulands Posten, and you're going to start making claims about all this stuff you learned. And this is okay because it shows that even if I delete these outlier points, the general structure of my model does not change. So you could go out and continue to make your claims about what you think is happening here and not be afraid that the results are significantly because of just a couple of data points. That's important. That's important, especially for job security. The last thing you want to do is go out and say a bunch of stuff and find out it's all wrong. And then maybe your job's on the line because you just made an idiot out of yourself. So that's kind of important. You don't want to make a bunch of strong claims and then discover that what you said was all wrong later on. So that's a good thing. But we're not done yet, right? So, okay, fine. The model maybe doesn't change that much without the points, but we're like, what do we do with these points? They're, they're just kind of outlying and we don't know what's going on and we don't have any good explanation for what's going on here. So let's take a closer look. Let's take a closer look at these data points. What are these data points anyway? What is going on with these? Okay, so let's take a look. Here we go. Let's look at the actual data. Let's look at the raw data for these data points. We can use that command again with the brackets. You can type in the name of the data set, square bracket, and a row number, and get a specific row of the data and look at it. And that's what I did here. So here we are, 64, 65, 71. Here are those three rows. Let's take a look. Okay, there's the data, looking good. Two data points look like they came from the exact same city or county because they have the same population and the same road, it looks like too. It's actually the same road segment. Actually, if you look at data point 64 and data point 65, they are both data points from two geographic locations that are very close to each other. And then you have data point 71, and it is a different geographic location because the population is twice as much. But the other characteristics are pretty similar. So let's take a look at this. What is going on with this data? So let's take a look at this look at this from each variable's point of view, and I'm going to jump to the chase here. Look at this. So all three of these have 6 lanes in the traffic. And if we go back to our residual plot for the number of lanes from before, from the panel, look at where these points are in that residual plot. In the number of lanes plot, these 3 points are all the most extreme in the number of lanes plot. And if we look at the number of lanes plot, the level of 6 lanes is the most influential to the fit of the model. it's also one of the smallest groups. The only one that has fewer is 8 lanes or 5 lanes. I mean, 5 and 8, those are really oddball. Even for America, 8 lanes in Wisconsin in Minnesota is a lot. So the 6 lanes is a, it's an outlier in the sense that it's a set of data that maybe doesn't fit with the rest of the data. It maybe doesn't really fit in this data set. It's like the Finland guy coming to Copenhagen. It's like, how many of those are there? And so this is maybe something to consider, right? This is something to consider, and that if we think about this, what is going on with the traffic flow? What is going on with the traffic flow based on this residual plot? What is it about the number of lanes 6 that's causing the residuals to be so extreme? And if you think about this just in terms of your knowledge of roads and your knowledge of traffic flow, what could be going on here? This is where you want to bring in your knowledge of the world into your analysis. You don't want to be just focused on the mathematical equations. You don't want to just be looking for the answers from the Cook's distance or from the coefficients in your regression model. You need to bring in the outside knowledge so that you can comment on what the model is telling you in some kind of intelligent way. Otherwise, you're just a slave to the equations. Then you're not bringing intelligence to the discussion. If all you do is run the calculations in your computer and report the results, you don't need a college education to do that. We could just hire some guy and teach him how to run the keyboard and make him do the numbers and then, be done with it. You need to bring in your other knowledge in order to make sense of what's going on with this analysis. So my question to you would be, based on your knowledge of traffic flow and based on your knowledge of motorways, why would a 6-lane motorway possibly produce these kind of oddball results? What kind of things could be going on here to produce these really strange swings in the residual values? Any thoughts on that? You guys do any deep analysis of large motorway flows in your other courses?
Well, you either have free-flowing traffic or you have extreme traffic jams, probably.
Yeah. And I think another very valid question to ask is, in what types of situations will you have a 6-lane road? Right? I mean, right there, you're immediately making some statements about what the environment is. It's not coincidental. It's not random. I mean, there's a 6-lane road there, and that immediately says there's a certain thing going on. And you kind of automatically know, once you hit a 6-lane motorway, that you're in an environment where there's already a history and a knowledge of traffic fluctuations. And, as opposed to a 2-lane road, right? I mean, there's gonna be a big difference in the behavior of the E47, right? The E47 ring road versus what is it? motorway, or it's not really a motorway, is it? It's Lanavai 257 to Gillelai or something, right? I mean, there's just like, totally different behavior, totally different kind of traffic flow, and totally different kind of traffic demand on those two different roads. And much higher probability of big swings, big variances. So one of the things we see here in this picture is variance, a lot of variance. You got a lot of variance here, a lot of swings. It has both the highest and the lowest traffic. It has both. It is negative down here at the most negative, and it is positive at the most up here, the highest variance. So, and then you think about traffic flow equations and how traffic fluctuates according to vehicle speed and density and all these things. And you think about the 6-lane motorway and you're like, yeah, that one is the one that's going to attract all of this mess. It's going to really be a strong candidate for a lot of variation, a lot of stuff going on. So there's a lot of kind of practical knowledge that you might say, this 6-lane motorway is going to be a real catching point for a lot of crazy behavior. And then you have to, think about this data set also in terms of cause and effect. So we have number of lanes as an independent, as an X variable in our traffic flow calculation. And then you start to ask questions like, well, is the number of lanes causing the traffic, or is the number of lanes a result of the traffic? That is, we have a 2-lane road, a 4-lane road, 6-lane road. Well, did the traffic increase because I built more lanes, or did I build more lanes because the traffic increased? And we have things called induced flow. And we also have things like, if you have parallel roads and you make one road bigger with more lanes, suddenly it becomes more attractive. And then other traffic from the parallel roads moves to the bigger motorway because it's suddenly more desirable. There's no mention in here, I don't believe, if I recall. Actually, let's take a look. Let's go back to the beginning here. What's missing in this data set, now that I think about it? Yeah. What's missing in this data set in terms of route choice? There's something really important missing here. There's something missing here that suddenly occurred to me, kind of important in terms of route. What's that?
Marriage?
Sorry?
Marriage status.
What stat? Oh, you mean the status of the driver?
Yeah.
No, that I think would be not significant. The marital status of the driver, probably not significant.
Oh, okay.
The speed. How fast is what is the speed limit on the road? Because in my mind, the higher speed limit road will be more attractive for traffic, right? If you're driving to Roskilde, Frederickson, or whatever, well, we don't have that many choices. I'm trying to think, where do we have a choice? Maybe, well, you kind of have a choice. Okay, you have a choice, for example, to Helsingør. If you're driving from Copenhagen to Helsingør, or maybe from Valby or Glostrup, where I live, you kind of have a choice. It's not, I mean, the first choice is obvious. Go up the E47, right? It's the fastest, normally, highest speed limit. That would be the dominant choice, and that would be where the traffic is going. But if for some reason, if there was a blockade on the road, it was closed, I don't know, something else, you might go up the Hillerød motorway and then swing over through Fredensborg, right? Maybe. Not the best, but but you wouldn't. And the reason you wouldn't partly is the speed limit, right? You'd want the higher speed limit, and the E47 has the higher speed limit. So that's why you would choose that road. And so then therefore you would say, well, maybe that's one of the reasons it has more traffic. So we're missing in this data set, it doesn't tell us what the speed limit on the road is. And it would seem to me that roads with a higher speed limit would attract more traffic. They would be more desirable. They would be, by definition, more desirable. I think the speed limit would actually almost be more important than, well, maybe not more important. I don't know. I think the speed limit would be an important factor. And I'm sure these roads have different speed limits. They're not all the same speed limit. Very definitely, especially the 2-lane roads. The 2-lane roads probably have a lower speed limit than the 4-lane roads. I'm pretty sure of that. And then, well, they have this functional class. So the interstate versus the non-interstate. So the interstate would probably have a higher speed limit than the non-interstate. But rather than vaguely state it as just kind of a class, it seemed to me much more clear and direct to just say, what is the speed limit, instead of hiding it, because the functional class, it is related to the speed limit, but it's not absolutely proof of what the speed limit is, because they're not, the speed limits can still go up and down within these different classes of road. So it's not exact what the speed limit is by saying, okay, the functional class, like urban interstate versus rural interstate. Well, yeah, there are guidelines for what the speed limit should be on those, but they're not fixed. There can still be different speed limits for those different classes. So anyway, my point is that when you're looking at this data and you're looking at these results, you need to think beyond just the data from the analysis. You need to think, okay, what are the other factors that are causing this data to behave the way it does? And you may come up with answers like, we collected the wrong data. we collected the wrong data. We've got the wrong stuff. It's, you know, we can't do anything with this because it's the wrong data. It's not helpful at all. And we need to go back and collect new data because this is not the right information. We didn't ask the right questions. That's the kind of thing you need to think about. And, you know, is it correlation or is it causation? Is the X variable actually causing the results that I see, or is the X variable just naturally correlated, just naturally the result of what I see, and therefore I haven't actually proven anything? Those are important questions. So summary here, you know, I've given you some tools to really look more closely at these residuals and to look more closely at your model structure. And if you were to actually go forward and do something involving data with a transport project, in your Outgangs project, for example, or in another course, or maybe in your pratique or something, you need these tools to do more. You don't want to just like throw the data in, hit go, calculate a result, say, I'm done. I got an answer. I'm all done. Here you go. Thanks. No. You need to look at it more carefully and really think, does my data really fit this model? Have I really thought about what the data is coming from? Have I really looked at possible other explanations for why the data is behaving the way it does in my model? Have I really thought this through? What's going on here? Can I really argue and defend and prove that things are happening the way I say they are? And so these are some of the tools that you can use to really dig deeper and prove that point with your data set. Next time, we are wrapping it up here. Next time is the standard course evaluation. And then I will give a review of our topics and prepare for the exam in next month. And one thing I didn't put on this slide, but I would like you to do, I'm going to open it up here. Let me slide this open and this, and I'm going to post this here right after we get off the screen. I'm going to post this. I would like you to read this paper. Let me pull it up here. Almost, I got it. Here we go. Where is it? I'm going to post this right after we get off the screen here. Here we go. Here we go. This paper from 1997. I'm going to post this, and I'd like you to read this for our class next week. 20 years of land use impact from the development of a transit system in San Francisco. And this paper uses some regression, uses some linear regression in the second half of the paper to argue some of its points. And the questions to think about here that I think to discuss are, number one, are the results in the conclusion of this paper really, are they defended from the regression analysis that was done here? And then, is the data appropriate for this regression analysis? And what more could we be doing to collect data to really answer the questions posed by this problem, by this paper? For example, the question here is, did the transit system actually lead to better economic results for the San Francisco Bay Area? And so I'd like you to read this. Let's talk about this next week, and as part of our wrap up for the exam. And then that'll close us out for the semester until exam time. So thanks a lot. We're all done here. If there are any questions from anybody, I will get to grading your homework and send them in, so you'll have those answers for next week. And then we'll get started on reviewing the material and taking exam in May. So I've had a couple of emails from folks about the exam date. I just want to clarify one more time. We do have exam on the date as it's written in the DTU calendar. Our exam date is, one more time, I'm just going to verify this one more time just to make sure, because there have been some confusion about this. It is not changed at all. Our exam date is Tuesday, the 18th in this class. And it will be online, and I have to write the exam and then submit it. This will be a new experience for me because I have not used this system before, but I believe what happens is I write the exam and I submit it to somebody else, and that other person actually enters the exam into the online system. So we'll see how that works. It's not part of DTU Learn. It is, the exam does not happen. This final exam does not happen on DTU Learn. It happens on this DTU exam system. So we'll see how that works. And it has an external sensor for evaluation of the exam and things like that. So anyway, see you next week, and thank you very much. And we'll close it out here.
Steven,
Yes.
can I ask you about the method you used? Was it Cook's method or something?
Cook's distance. Yeah.
Cook's distance, yeah. If we were to find another way to find these outliers and use that method in the exam, would that be okay?
Well, tell me about it.
I don't know it yet.
Okay, you don't know it yet.
Usually, usually there are other methods to doing these things.
Well, I guess the question would be, is it another method that actually gives a different answer, or is it just another method, right? I mean, if it's if it's uh if it's uh if it's a different method but it gives the same answer, then I guess it's not wrong, but then what's the point, right? I mean, I just showed you how to do it one way. Commands are all there.
Yeah,
Job
but
done,
it's
right?
also it's a more general question about other methods in
Yeah. There
because
are,
there are many ways.
for example, I pull out my favorite old book for regression. And, if I go to my old book, there are some other statistics that you can look at. There's one called PRESS, P-R-E-S-S, and there's one called DF, let me look it up here. Here we go. There we go. So there are, for example, the DFFITS, DFITs, and DF betas. These are more obscure. They have different functionalities. Yeah, there's something called the influence on the regression coefficients, but what would they, I think we're just confusing everybody else in the class by even talking about this right now. But yeah, there are some other things you can do for sure. Leverage values. I didn't talk about leverage values. I did not talk at all about studentized residuals or things like that. I mean, these are all more advanced topics, and I just, so yeah, are there other things you could do? Yeah, if I don't even know if we'll have a question where that will come up, to be honest with you, in the exam. But
oh, so that's a hint.
I mean, will we have a question in the exam that asks you to talk about outliers? Absolutely. Will we have a question in the exam where it's at such a level of detail that you really, will we have a question in the exam where you ask to discuss what the point of having a Cook's distance is? Yeah, sure, why not? That sounds reasonable. Would you have a question in the exam where there would be a reason for you to start discussing any of the other points, other ideas I just listed? Maybe, but I can't predict that. I haven't written the exam yet. I'm going to write it this coming week. I guess for the other people who are listening to this right now, my answer would be, don't worry about it. Focus on the stuff that was in the slides. That makes it easier for everybody. It's easier for you to know what you have to study. It's easier for me to write the exam and do stuff like that. Yeah, are there other things we could learn? Absolutely. Are there more things in your textbook that you could read about? Absolutely. But we set a limit to fit the time we have and to kind of keep a nice even playing field. So I will only hold people accountable for the things that we've actually done in the lessons and had in our learning objectives. And I won't be, that's icing on the cake, so to speak, as we say in English. If you can do the basic things that I ask for in the questions and the discussion, and then on top of that, you suddenly have all this extra knowledge, great. But I'm more concerned about the basics. Make sure you got the basics covered first. And then after that, if you've got other great ideas, that's fine. So
also is it possible to get more not assignments, but opgaver?
Yeah.
That resembles somewhat resembles the opgaver that
I guess the answer is unfortunately no. unfortunately,
Oh, great.
the text, I mean, what you mean is you upscale with loosening, upscale as examples with answers. And
Yeah, that
I
would
don't
also
have
be
any
good.
more. I mean, I'd have to actually do the solutions myself to distribute them. And that is actually a criticism I have of this book. And I said that earlier in the semester. One of the things I don't like about this book is we actually do not have like exercises in the book that I can give as assignments that have answers. And I agree that that is something that we're missing. And unfortunately, and I don't see any evidence from the previous course, the previous teacher of this course did not teach this class in such a way that there were also sets of problems with answers. The previous teacher of this course taught it in the more kind of DTU way of it being a project-based course. And it was like, you know, he taught some of the theory and some software, and they said, okay, everybody make a project. And, you know, project work is nice, but to be honest with you, I think you guys missed something in your education by having so much project work, because it leaves a lot of opportunity for you guys to actually not be tested and not really have certain skills clearly learned. It leaves a lot of opportunity
Yeah, that's true.
to get through and do a project and actually not even know how certain things work. And so I actually think it's a good idea this time that I'm teaching this class in such a way that I say, nope, here are the skills, and you need to check the box and show me you can do these skills. And but I agree, it would be nice if we had more problem exercises with solutions, and I don't have them from your textbook, and I just honestly don't have the time to generate them myself. It's the kind of thing that I would accumulate them over many years, and I just wasn't able to do it in the you know, in the 2 months of preparation for this semester. I can't do it. I think
it's understandable.
Yeah,
So,
there are some data sets in the book to play with, and there are basically every table, every sample example you see in the book, the data set, if you would like to practice with, if you see an example in the text that you would like to reproduce, that you would like to try, I can get the data set. There's an online website. I mean, actually, you know, it's not even a private website. I can just send you the link. I'll just post the link. You can download the data sets that the authors use for their examples in the text and try it and see if you get the same answers. So I can post that. I will do that because it's not password protected or anything. It's basically a public website. And so you can get the data sets for the examples in the book. That is there. That is definitely there. Yeah.
okay. Sounds great. Yeah, those were all the questions I had. So.
Thank you. All right, everybody.
Can I ask you something not related to this subject, Stephen?
Yeah.
It was just some of the old colleagues I have gave me the I don't know what's saying udbudsmateriale to the new S trains.
Yeah.
But it's a fairly large PDF file. I was wondering if you wanted a like copy.
I'd love it.
But I don't know how to share a copy of a PDF file that's too big with you. So
you can, I think you could post it to our class website.
Yeah, I could do that maybe.
I think you can. I think you can post things to DTU Learn.
Yeah.
You could just lie and say it's a homework assignment or something, or, you know.
Yeah, exactly.
You know, anywhere. One of these, let's see here. That's a good question. I think there is a place for you to just post things. There's like a discussion area or something. But anyway, how big is it?
I don't know. It was too big to email it. That's all I got.
There is
but I can try and upload it on Learn. Otherwise, I can just send you an email and ask you how to do it otherwise.
Yeah, I mean, there are different ways we can do it. I've got Google Drive and I've got all these things.
Yeah.
But yeah, there must be. I think there is, yeah, anyway, there must be a spot, or I can create a spot. Maybe if I create a fake assignment and say, submit your answer to the assignment. That might be one way to do it. Oh,
You can
and,
do
and
that.
oh, and Milal says we should be looking at files DTU. You're probably right. You know, I never use files DTU, but it's there, isn't it? Why can't we use that? Absolutely.
If it's easier, just do an assignment either here or in freight trains, and then I can just submit it.
Yeah. Yeah, actually, Milal's right. I mean, we have this files DTU. I've used it like twice in my life. And for some people, it's really important, right? I mean, if you need to share enormous amounts of files and it's too big to fit in D2 Learn, then this is the way to do it. I just have never had a need for it. But yeah, try this. Yeah, let's do files DTU.
Okay.
That sounds like a winner. And looks pretty. You just log in and you say upload, and then I guess you make a shared folder and put my name on it so I can see it or something. And
yeah, I can try that. I just thought that maybe there's something that interests you.
It probably does. Yeah, absolutely. Absolutely. Hey, well, I'm gonna stop recording because the rest of the world doesn't want to like hear all about what everybody else. Goodbye. Tui and I are going to talk about trains for a minute.